I'm Avramaki, and I'm going to present LARI, which is a practical data center network topology which allows racks to dynamically adapt their aggregate uplink bandwidth according to their traffic demand. So first of all, let me talk a bit about the context. In today's data center networks, 40 gigabits is the norm, while we are already at a stage where we can deploy 100 gigabit links. However, as the server bandwidth increases, the cost to support full bisection bandwidth becomes prohibitive. As a result, oversubscription seems inevitable in order to reduce the network cost, but this can have a significant impact at the performance of the system. So the question is, do we really need provision data center networks for peak performance? Several recent studies have observed low average utilization and highly skewed rack-level network traffic demand in today's data center networks. As a result, network flexibility is important in order to handle the peak demand in oversubscribed networks. And this can be achieved in two ways. First of all, network configurability allows network topologies to dynamically adapt to workload changes. This is typically achieved by adding new technology, such as optical circuit switches and free space optics, at the core of the network. In these approaches, ad hoc links can be created in order to alleviate hotspots. For example, in a fully reconfigurable data center network topology, high link bandwidths can be established between any pair of doors in order to offload traffic. However, these approaches typically involve substantial changes to the control and the data plane, and this hardens their transparent and incremental deployment. Alternatively, flexibility can be achieved using sophisticated traffic engineering on top of flatter topologies. However, these approaches are not incremental or transparent because they require recabling or custom routing policies. More importantly, in these cases, non-shortest path routing typically introduces additional forwarding latency of a few hundreds of nanoseconds per hop, which can be prohibitive for latency-sensitive applications. So, despite their efficiency, these approaches have real-world challenges, which actually is the reason why they have not been implemented in existing data centers. But do we really need to change the entire data center network in order to achieve network flexibility? In LARI, we propose local configurability, which operates at a scale of 2 to 6 racks. A deployment unit of a few racks allows for transparency and incremental deployment. The idea is to allow racks to dynamically adapt their aggregate uplink bandwidth using spare bandwidth from a small number of physically adjacent racks. LARI is based on two key observations. First of all, we observe that due to topological reasons, there are spare ports on the top of rack switches. Additionally, in traces collected from our data centers, we observed that the rack level traffic is bursty and loosely correlated across racks in some of our workloads. So, let's see now how we can deploy local configurability. In a traditional data center network, each top of rack switch is connected to a set of aggregation switches using a fixed number of SATCAP links. So, local configurability can be implemented by enabling non-shortest path routing between the doors and the aggregation switches. This can be achieved by directing server traffic by forwarding the server traffic directed to the aggregation switches through other TORs or other servers in the rack set. However, this involves additional NIC ports and custom routing policies. Alternatively, we can directly interconnect the top-of-rack switches using their spare ports. But this could lead to, there are scenarios of fate sharing. Or otherwise, we could add an additional layer of packet switches on the top at a higher cost. More importantly, all these approaches introduce additional forwarding latency per hop, which actually affects the end-to-end latency of the applications. Instead, local reconfigurability can be implemented at the physical layer. In LARI, we use electrical circuit switches which operate at the physical layer by forwarding an electrical signal from one port to the other according to the established circuits. An electrical circuit switch has typically low cost because it doesn't involve any packet buffering or packet processing logic. As a result, this adds only a small, predictable end-to-end forwarding latency of 2 nanoseconds. So, in LARI, we keep a set of the top-of-rack uplink statically wired to the aggregation switches. And we do that in order to ensure the network connectivity in case of failures. Then, we connect the rest of the uplinks to a circuit switch. And for each one of these links, we also connect a port of the circuit switch to the aggregation layer. Furthermore, we also connect any spare top-of-rack switch port to the circuit switch. In this way, we allow the top-of-rack switch to get a configurable uplink bandwidth according to their traffic demand. For example, here, we can decongest TOR-M by migrating an uplink from the first top-of-rack switch after configuring the switch. So, the design of LARI allows for transparency because we only need a small local controller, local to the rack set, which operates transparently to the rest of the network. Additionally, it is a cost-efficient solution because we do not require any additional cables to the aggregation layer, but we only need any extra cabling can be achieved using spare top-of-rack switch ports and passive cables to connect the top-of-rack switches to the circuit switch. This design, despite its simplicity, actually is not practical due to the limited number of ports in the available electrical circuit switches. Instead, we distribute the reconfigurable fabric across the racks in the rack set. More specifically, we use a circuit switch per rack, and we ensure that each top-of-rack switch is connected to all the circuit switches in the rack set. Then, we distribute the links to the aggregation layer across all the circuit switches. Each TOR has 2 uplinks statically connected to the aggregation layer, and we distribute equally the rest of each uplinks across the circuit switches. Now, in the control plane, we use a simple soft-state controller within each rack set, which is responsible for the traffic monitoring and the configuration management. The controller is local and requires no information from no global information from the core network, and it simply uses per port traffic statistics delivered from the top-of-rack switches in the rack set. Our configuration policy is conservative and it targets to minimize the reconfiguration overhead. And finally, any reconfiguration events are only visible to the top of rack switches and the aggregation switches as link failures and link repairs. And the controller can manage these events either explicitly or implicitly. You can find more information about the reconfiguration policy in our paper. Now, for the performance evaluation, we have implemented a prototype circuit switch, and we evaluated its performance using a small testbed. We also ran large-scale simulations using a custom flow-based simulator. For the simulated topologies, we use 32-port top-of-rack circuit and aggregation switches, which operate at 100 gigabits. And we use 32 servers per rack with 50 gigabits per server. We use micro benchmarks and real-world traces collected in our data centers in order to evaluate the performance of LARI. And we focus on the switching time, the 99th percentile flow completion time, and the performance per cost. So, we built a prototype circuit switch with 40 ports at 40 gigabit. We measured the switching time of our prototype by connecting an oscilloscope to 2 ports of the circuit switch. Initially, we set up a circuit between a packet switch and the first port of the oscilloscope. And then we measured the time needed to reconfigure the circuit from the first port to the second. We ran multiple repetitions, and we found that the switching time, the time needed to establish a circuit, is on average around 18 nanoseconds. Now, we will try to understand the benefit of deploying LARI over a statically wired network topology. For this reason, we examine statically wired network topologies with a fixed number of uplinks to the aggregation switches according to the oversubscription as presented on the x-axis. We also consider LARI with the same oversubscription, and for each door we use 2 uplinks to connect to the aggregation layer and 3 ports per circuit switch in the rack set. For our evaluation here, we use 2 different sets of traces. The first one captures the file accesses of a large-scale storage service. And the second trace is from a production data center and was previously presented in the projector paper. So in these plots, we focus on the 99th percentile flow completion time, and we can see that LARI can achieve lower flow completion time even at high oversubscription. For example, with oversubscription 3.2x, we can see that LARI can improve the flow completion time of the static topology by 64%. Additionally, we can see that at the highest oversubscription, LARI can improve the tail performance by a factor of 2. And similarly, we can see the same trend in the second workload race. So at this point, it is important to note that in today's data centers, we are interested in oversubscriptions between 2 and 3.2x. So the next step now is to understand which are the cost implications of deploying LARI. Intuitively, LARI requires additional ports and cables at the rack level. So in this experiment, we try to understand whether the cost benefit is worth this extra cost. In these plots, we evaluate the deployment cost of the entire data center using a cost model which includes the volume costs of the cables, the merchant silicon, and the server NICs. each data point here corresponds to a different oversubscription, varying from 1 to 5.3 in increasing order from right to left. On the x-axis, we saw the estimated cost normalized to that of the fully provisioned data center network topology. We can see in both workloads that given a target flow completion time, in most of the cases, there is a Larry configuration which is able to meet the performance goal at lower cost. So, overall, we proposed local reconfigurability, which can be achieved by migrating by uplink migration within small sets of physically adjacent racks. The proposed design can be deployed incrementally and operate transparently in existing data center networks using low-cost electrical circuit switches and a small local controller local to the rack set. Using alternative workloads, we showed that local reconfigurability is able to improve the performance per cost of the traditional oversubscribed networks by a factor of 2. And this concludes my talk. Thank you.
All right. I'm hoping maybe an operator will ask a question. There's no rule preventing us from asking questions to the audience, I don't think. So we should, if anyone wants to, okay, Rocket, great. Well, that's close.
Why not? So thanks. I think this is great work and exciting one. I'm actually a little curious. We spent a lot of time trying to understand how does the cost of circuit switch compare to packet switches, and I know that Ant has talked in the lab a lot. But I was curious if you had more insights about. I think what you said is circuit switches are cheaper because they don't have to do packet buffering. And I'm curious, do you have some insights about how the cost breakdown looks like across I/O and silicon? And could you give us some more insights about the cost of circuit switches?
Yes. So, the main difference between the electrical circuit switches and the electrical packet switches is that, first of all, as you've mentioned, they do not involve any packet buffering or packet processing logic, which simplifies the design of the hardware. So another important factor is that, which affects the cost, is that in the electrical circuit switches, we do not need to demultiplex the high bandwidth serial data link to lower speed lanes. And this is another factor that significantly affects this cost benefit of the electrical circuit switches. But the truth is that we cannot do a fair comparison because there are other parameters that we should take into account. For instance, it depends on the volume of the production. So we don't know how this can evolve, but the truth is that we've done a sensitivity analysis on the cost of the electrical circuit switch. So you can see in our paper the experiment where we explored the circuit to the packet switch per port cost and cost ratio, and we've seen that when this is lower than 1.2, it's the electrical circuit, the Larry is able to achieve the same performance at much lower cost. So I cannot break down the cost of the electrical circuit switch further, but this already gives us an insight of why we expect it to have lower cost on the electrical packet switch. I don't know if I answered your question.
He gave a thumbs up. I'm curious, what is sort of the next step for this work? I mean, are you going to try and deploy it at Microsoft, or what do you sort of see as the next hump to get over?
The main I think that the most important thing in this work is that it is very easy to deploy it in small scale. So, for instance, if a cloud provider faces congestion in a specific service, then Larry can be deployed across the racks that run this service and without affecting the rest of the network. So it will operate transparently to the rest of the network, and it will simply help the cloud provider to get a better uplink bandwidth management. So the next step is to evaluate small-scale deployment, maybe, and see how it goes. And there are optimizations also that we do have in mind in the control plane and things that we can do better regarding the load balancing and such things.
All right, well, let's thank our speaker again.